Hi, I'm Brian Mullins, and this is Balls Out Physics, Episode 2, The Gravitational Constant. Before I begin, I really want to thank everybody who commented on the first episode. The positive feedback was fantastic. I had no idea the video would be so well received. Thank you all for taking the time to watch it and really think about it. And even in some of the negative comments, there were some very good questions asked, and I would definitely like to revisit the plane problem after a few episodes. But there's some topics I'd like to cover first because I think it'll better explain the plane problem as we go along. And so the other thing I want to say is that I'm not claiming to be right about all this. When I first discovered flat Earth theory, I thought I could debunk it right away. But the problem was I couldn't. I realized that there were some very good points being brought up by the flat Earth community, and that's why I started this series, because I'm really asking for help here. I can't explain these things, and I've got a pretty strong physics background. I took 2 physics courses in high school and then a bunch in college to get my degree, and maybe I'm missing something, maybe I'm not. But one of my favorite sayings in the engineering world is, you learn 10 times more from your mistakes than you do from your success. This is what we always tell rookie engineers. This is what they told me. Don't worry about making mistakes. Don't worry about being wrong. Because when you are wrong or you do make a mistake, you want to find out why. And on the way to finding out why, you learn a ton. So never be afraid to be wrong.
Well, hi everyone, and greetings from northern Michigan. This is Bob the Science Guy. It's rainy and cold here in Michigan, so I'm going to make things spring-like with my nice tropical shirt. Now, today we're going to deal with my favorite flat Earth engineer, Mr. Brian Mullins. And we're going to discuss how the gravitational constant was determined. Now, the cool thing about this is Brian seems to be of the opinion that this was just made up so that something would fit. But we're going to go through his math and have a look at it and see whether or not maybe he might be wrong on that. So let's cue up the music and hit the road.
This episode is mainly about gravity, but it's about the gravitational constant in the gravity equation. However, to get there, we need to start with some basic physics. And so I've set up a problem here with the Earth, represented by this blue ball, and me or any other man or woman standing on the Earth, and how we determine the weight of that person, okay? Or the force of gravity acting on that person. Weight and the force of gravity are actually the same, or at least that's the accepted belief in physics. Weight is actually caused by the force of gravity of the Earth pulling down on the object in this case. The bread and butter physics equation up here, one of the first equations you learn in Physics 1 is force is equal to mass times acceleration. This is what Newton based all of his 3 laws of motion on. And since his boy Copernicus, 150 years prior, had come up with the solar system, he knew that he needed to come up with an equation that would not only work on Earth, but would work throughout the universe. Okay? And so what this equation says is that the force acting on an object is equal to the mass of that object multiplied by the acceleration that the object is experiencing. Okay? And mass is defined as the amount of matter in an object. And in Physics 1, they hammer into your head that mass is the same throughout the universe. Only weight changes because the gravity on each planet can change. The gravity on the moon is less than it is on Earth. It's supposed to be about 1/6 of what it is on Earth. And so I was taking physics, and I had just taken chemistry, or I was taking it at the same time, I can't remember. But I immediately thought about the fact in the lab we were weighing things in terms of grams. And in the metric system, grams and kilograms are actually units of mass. But to determine mass, we actually weigh it, or weigh an object, and we say this is how massive it is. And so I thought to myself, well, if that's the case, if I took that same scale up to the moon, it would definitely give me a different reading because the force of gravity is less, and that's what's pulling the scale down, right? So how can that be? How can mass be the same throughout the universe? Does that mean we would have to calibrate our scales to work on the moon so that they show the same mass that we get on the Earth?
Now, Brian, here is your first error in judgment in this video. Now, as you correctly point out, weight equals mass times gravity. Okay, weight is a force because there is a mass and an acceleration, in this case, the acceleration of gravity. Now, there's two ways that we can measure weight. Let's go over the first one. Say we have a known mass right here, and say this is, say, 500 grams. Now, we can place that on a scale that has a spring in it. And the mass of this 500 grams will be pressed down by the acceleration of gravity. And the product of that will be measured by the scale in newtons. A newton is 1 kilogram accelerated to 1 meter per second squared. Okay? Now, in this case, the problem that we're going to run into is that this gravity right here is not the only force that is involved. Now, on the Earth, which is a rotating sphere, we also have centrifugal force. And that is maximal at the equator because that's where the velocity, the linear velocity of the Earth is the greatest. Now, I'm going to show a nice demonstration of this in a moment, but let me explain the background of it first. When you have a rotating object, you're going to have a centrifugal force. Say, here's our rotating object. We're going to have a centrifugal force going away from the object, and then we're going to have a force of gravity going towards the center of the object. They're opposing forces. Now, on the Earth, with our rotation, things weigh a little bit less at the equator than they do at the poles because of this centrifugal force pulling the object away from the center of the Earth and opposing the gravity which is accelerating it towards the center of the Earth. Now, as a result of that, if we calibrate this spring scale right here to 500 grams at the equator, and then we take the same 500 gram mass and the same scale without touching it and bring it up to, say, 45 degrees north, that 500 grams may weigh 530 grams. If we take it up to the North Pole, it may weigh even more, 550 or 560 grams. Now, how do we get rid of this? And this is the way we do it in science. Now, in your lab, you probably had some very delicate spring balances that you weighed things. And you'd put a 500 gram mass on that. It would be calibrated to read 500 grams for that. And the amount of downward acceleration that this mass was undergoing would be set at that lab. So very obviously, anything you weighed on that calibrated scale at that location could be read off in grams times the local acceleration of gravity. So rather than do the full equation and come up with the number of newtons, which is the grams times the acceleration, that scale may be calibrated in such a way that it gets the reading in newtons and then just automatically converts it and gives a reading in mass, and that mass is what is being read out on the scale. And that's fine if you're doing something locally. But say you're weighing diamonds, or you're weighing a precious metal like gold. Okay? How would you create a scale that would work anywhere and give an accurate reading in mass without regard to the downward acceleration of gravity being opposed by the upward acceleration of centrifugal force due to the rotation of the Earth? Well, that's pretty simple. What you do is you get something that looks like this. And that's called a balance scale. You put your 500 gram mass right there, and then you weigh your test right there. And if this scale balances, if this is 500 grams, so is that. That's called a balance scale or a beam balance. That's what you use for accurate determinations of mass, because it directly compares one mass, a known mass, to an unknown mass. A balance scale is the most accurate way of doing it. A spring scale, like you're talking about, is fine if you're just using it in one location and it's calibrated to that location. Now, Brian, here is a big problem that I have with your presentation so far. You've had physics and you've had chemistry. You know the difference between a beam balance and a spring balance. Now, what you just said was that if you took your little spring balance and moved it to other planets that somehow and got different readings, that would somehow mean that mass was different in other locations. You know that's not true. You know that mass is mass. What is the difference? Mass, or weight, shall we say, is mass times gravitational force or acceleration. You know that different planets like the moon, Mars, the Earth, all have different accelerations of gravity because they have different masses. Now, they will give a different weight based on your spring scale, but if you use a beam balance on those planets, 500 grams is 500 grams one way or the other. It doesn't matter what the acceleration of gravity is. Why would you even suggest that mass somehow was not the same, when the difference clearly was the acceleration of gravity that you were using in your weight equation?
How does that work? Does that mean that just all mass in the universe is actually defined on Earth? I don't know. I never really got that, but at the time I had been in school for a long time. I was 18 years old and I was ready to get out and go make some money, so I didn't really ask too many questions.
Brian, you're kidding, right? That was your approach to the profession of engineering. You didn't understand it, but you wanted to get out and make some money, so you didn't ask any questions. That just shocks me.
However, I always questioned that, and I always thought about it, and I've talked about this with some other people, and there are a lot of people that say, yeah, that doesn't really make a whole lot of sense, but it's accepted in the physics world. So anyway, that's mass. Okay? The mass of an object, the amount of matter in an object. The acceleration is defined as any change in velocity. Okay? So velocity can be measured in miles per hour, as I did show in the first problem, or kilometers per hour, kilometers per second, meters per second, whatever. That's the rate of velocity. However, acceleration is defined as any change in velocity. So in this example, if I'm standing right here on this Earth, okay, I have a velocity. I'm moving with the Earth. As you remember in the first problem, he said, I'm in Central Florida. My velocity is probably around 900 miles per hour, maybe a little less, somewhere between 850 and 900 miles per hour. Okay, but since the Earth, I'm supposed to be standing on an Earth that is rotating. This direction of that velocity is constantly changing. Okay, so when I get over here, this is exaggerated, obviously, but now my velocity is pointing this way. So, even though I'm standing at rest, because of this theory, I'm constantly accelerating because the direction of my velocity is constantly changing. And this will be better explained in the next episode when we talk about centrifugal force.
Okay, well guys, I don't know about you, but I'm kind of getting the impression that Brian is struggling with some of the very fundamental properties of physics, like what is mass? What's the difference between a spring and a beam balance? What does weight actually mean, and what's the variable in objects that are of the same mass that weigh different things in different environments? So Let's go see where he's going from here. But right now, I'm not really comfortable with his grasp of the fundamentals of physics.
So anyway, since weight and mass are different, weight is actually considered to be a force. This force of gravity, we have weight over here and weight here. Weight is equal to the force of gravity pulling me down. Okay, so this equation can be rewritten. F equals ma can be written as weight is equal to mass times little g here, and little g is considered the acceleration due to gravity, or the acceleration at which things fall towards Earth.
Okay.
I posted a link in the description to a trailer for the BBC series episode 4, Human Universe, in which Professor Brian Cox from the UK, travels to the Glenn Research Center in Cleveland, Ohio, to do an experiment with NASA's vacuum chamber. And in the experiment, they drop a clump of feathers and a bowling ball. And the first time they drop it when there's air in the chamber, the bowling ball obviously falls a lot faster than the clump of feathers. But when they remove all of the air from the vacuum chamber, both the feathers and the bowling ball fall at exactly the same rate. So what this little g says is that all objects accelerate towards Earth at the same rate unless there is some type of fluid preventing them from falling at that rate.
Actually, no, that's not what it says at all. It says that weight equals mass times the acceleration of gravity. All right. It doesn't change anything there. The rate at which it falls can be influenced by opposing accelerations, such as the acceleration of wind resistance. Now, the way that you can tell that that's what's going on with the bowling ball and the feathers is you look at the mass of the feathers and their cross-section, then you look at the mass of the bowling ball and its cross-section. Obviously, the bowling ball has got a lot more mass behind a much smaller cross-section. As a result, it will be affected by the wind resistance less than the light, large cross-section feathers would be affected. This is basically a vector of force issue. Now, you can tell that it has to do solely with the wind resistance because when you remove the air from the chamber, they both fall at the same rate. That means the acceleration of gravity is uniform. However, there is a force opposing it, and that force in this case is wind resistance. Yes, air is a fluid, but I don't think that you're grasping the problem correctly here, but let's let you continue.
So the more dense something is, the faster it'll fall through the air. The less dense, the slower. It's just like in water. Something heavier or more dense, more massive will sink faster than something that's less massive or less dense. And if the density is actually less than water, it'll float. And the same with our air. That's how hot air balloons work. Or blimps with helium inside them, or balloons. That's why they float, because their density is less than that of air. But when you get rid of air,
no, actually, they float or sink based on the well-known factors of buoyancy. It's a relative density between the two objects versus the amount of displacement. And then you need gravity to provide the directionality and the acceleration. So, it's a little bit more complex than just a matter of density alone. So, go ahead and let's have you continue.
For any fluid, everything falls at the same rate. And that's a really great episode. I highly recommend you watch it. It's very interesting to see. Okay, so that's weight. Okay, and weight or force in the metric system is measured in newtons. Okay, so 1 Newton, obviously they give credit to the guy that came up with this, 1 Newton is equal to 1 kilogram times acceleration due to gravity, or rate at which things accelerate towards Earth, which is 9.81 meters a second squared. So,
no, actually 1 Newton is 1 kilogram times 1 meter per second squared. A 1 kilogram mass undergoing acceleration by the Earth's gravitational acceleration would weigh 9.81 newtons.
Squared. So 1 Newton is equal to 9.81 kilograms times meters per second squared. Okay, remember that a Newton is really equal to units of kilograms times meters per second squared. 1 is equal to 9.81. Okay.
Seriously, guys, don't take my word for it. There's the definition of a Newton. It's an SI unit of force. It is equal to the force that would give a mass of 1 kilogram and acceleration of 1 meter per second per second. So, a 1 kilogram mass undergoing the 9.81 meter per second squared acceleration of gravity would weigh 9.81 newtons. He's just got this definition wrong. Well, I'm going to go ahead and finish up this video with just a very brief demonstration from Brian on the use of the universal gravitation equation from Newton. And he doesn't do too bad of a job with it when he's plugging in the numbers. But then he talks about the gravitational constant. Now, before we get into his gravitational constant discussion, I'm going to go ahead and go over the Cavendish experiment tomorrow and how it was set up, where the variables were, and how the gravitational constant was actually determined. But let's let him go ahead and go through this one example just to kind of prep us for the discussion to follow.
I weigh about 160 pounds, and in the English system I could just say that's pounds mass, or actually I can say that's pounds force, but in the English system we don't actually differentiate between, with two different units between mass and weight. There is a unit called a slug that's used for mass but nobody uses it, or there is mass but nobody uses. So if I say my weight is 160 pounds force, I can convert that to mass in the metric system, which is about 72.6 kilograms. So my weight in the metric system would be 72.6 kilograms times 9.81 meters per second squared equals roughly 712 newtons. Okay? That's my weight in metric units.
Correct.
So, over here, we have the equation due to gravity. Okay. And that says that the force of gravity is equal to the gravitational constant times the mass of one object, in this case, me, this is represented by a little m, times the mass of another object, which would be the Earth, divided by the distance between them squared, which in this case would be the radius of the Earth. Now you should actually add the distance to my center of mass from the Earth's surface, but it's so insignificant that it doesn't really matter. Okay? And the gravitational constant, which I should have written down here, is equal to 6.67408 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay? So if you plug the mass of Earth, which I have written here, which is 5.9726 times 10 to the 24th kilograms, really big number, my mass, 72.6 kilograms, and the gravitational constant, and the radius of Earth, which is 6,371,000 meters, you will get 712 newtons, roughly. Pretty close. Close enough to say it's the same. To say that to accept the fact that, well, the assumed fact that gravity is causing this weight, and that's why I have weight is equal to the force of gravity on here. Okay? This is what is taught in physics.
Now that's a very interesting approach taken by Brian Mullins. He caught himself talking about facts of gravity and then had to stop himself because he's doing a narrative here for the flat Earth, and gravity cannot exist in a flat Earth. So he's now qualifying everything that he says of this is what is taught. This is the accepted theory. All right, these aren't just taught and they're not just the accepted theory. They're the way things are. And these equations work. Now, I think that tomorrow what we need to do is we need to have a real close look at universal gravity, according to Newton. And we also have to have a look at the Cavendish experiment. So before we go on with Brian, we're going to go ahead and have an episode on gravity and the Cavendish experiment tomorrow. And then we're going to continue with how Brian seems to believe the gravitational constant was determined. And just a little spoiler alert, he thinks it was just simply made up for convenience. We're going to show tomorrow how it was actually derived. And then once we have that, we can get our better assessment of what Brian is trying to talk about here. So this is Bob the Science Guy. I'm signing out from Northern Michigan. Please remember to like and subscribe to my channel. The button is right down there. Just click on that and that'll get you a subscription. Maybe hit the little bell so you get a notification when I have a new video out. So thank you very much for stopping by, and we'll see you tomorrow with the Cavendish experiment and the gravitational constant.
This rabbit hole's too deep for me.